All right, good afternoon. Welcome, my name is Matt Taylor. I'm a program co-chair. If you've been on the internet in the last year or two, you've probably heard about agentic AI. Well, Professor Peter Stone has been working on agents for a few decades on reinforcement learning, robotics, and multi-agent systems. Just last year, he was recognized with the ACM AAAI Alan Newell Award. Peter wears many hats. I know him as an amazing mentor and collaborator, but he's also a department chair and chief scientist at Sony AI. So please join me in welcoming Peter Stone for AAAI 26's first invited talk, titled From How to Learn to What to Learn in Multi-Agent Systems and Robotics. Thank you, Peter.
Thank you, Matt, for the kind introduction, and especially to you and Chad for inviting me to give this talk, to all of you for being here. So first, I'm going to introduce, I'm coming from the University of Texas at Austin, where there's some really exciting times. I was the founding director of Texas Robotics. We now have 18 core faculty who publish in the top robotics conferences, and we're hosting the conference on robot learning next year. I hope many of you will come. We have a beautiful space to house all of our robotics that used to be a gymnasium. We had one of the first NSF AI institutes, the Institute for Foundations of Machine Learning, that's chaired by Adam Clivens. And I'm really excited about also our campus-wide initiative on the societal implications of artificial intelligence, an organization called Good Systems that is inspired in many ways by the 100-year study on artificial intelligence, which I've played a big role in over the last decade or so. And we're waiting with bated breath for the next study panel report, which is due later this year, chaired by Mike Wooldridge. And at UT, we've also been a leader in AI education. I'm really excited about a new, very large-scale course on AI literacy that I've organized with some colleagues, including Joydeep Biswas, who's here. There'll be a talk about that at the AAAI conference on Saturday morning. And we've also launched a very large-scale online master's in artificial intelligence at a very affordable price. So as Matt said, I've been working on autonomous agents for several decades now. And I do a bunch of different things in my lab. But the question that unifies all of them is the one shown here. It's to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? And so the sub-areas of artificial intelligence that we publish in addition to being at the flagship conference like AAAI, are the ones shown here. And I'm going to focus especially in this talk on multi-agent systems and robotics, as in the title, and the type of machine learning that's become very popular these days, reinforcement learning, that I've been involved in for many years. Now, in my lab, we both do sort of fundamental, foundational, theoretical, and algorithmic work that I sort of call bottom-up research, and also more use-inspired research that's motivated by concrete applications. And so when I give a one-slide introduction to my lab, it's easier to talk about those domains that inspire me. And so one, over the years, has been RoboCup, the Robot Soccer World Cup, and this is a clip from several years ago. Our team is the robots with the ones with their arms behind their back, playing in a game against the team from the University of Bremen in the finals of a competition. And as you watch this, you remember that the robots are fully autonomous. They're sensing, deciding, and acting. Here you see our robot going in on a breakaway. And it'll calmly bank the ball off the goalpost and into the goal. We went on to win that game in the championship that year. Our goal, though, is by the year 2050, or one of the goals of RoboCup, the sort of founding inspirational goal, is by the year 2050 to have a team of humanoid robots that can beat the best World Cup champion on a real soccer field. And as you can tell from that, we're still quite far away from that. But there has been really big developments in recent years. In fact, this year was the first time that it made sense to have a demonstration game with robots and people, humanoid robots and people on the same field. We've done robots and people with wheeled robots for many years, but this time we did people and humanoid robots. It wasn't very interesting at first when it was people against the robots, so after a few minutes, I moved over to the team with the robots. And I'm going to show you a clip that could not have happened a year ago. It's using a fantastic robot from Booster. And so at the beginning of this video, you'll see that I have the ball. I'm actually right in front of, again, my colleague Joydeep Biswas. I go around him, and then I leave the ball for the robot, and I had no idea what was going to happen. But it was huge, so watch this. So I leave the ball for the robot, and the robot turns and kicks the ball into the goal through the legs of Ubo Visser, the current president of RoboCup. And like I say, that could not have happened a year ago, I don't think. And so I think it's really exciting that we're getting to this point where it actually makes sense to, it's not crazy to have people and humanoid robots on the field together. Anyway, we're still a long way from that long-term goal. RoboCup isn't just about soccer. There's also a part of RoboCup called RoboCup at Home. Here you see a robot that's doing things like acting as a party host in a sort of social robotics setting that has to manipulate dishes in a kitchen, has to put away groceries and try to figure out for itself which groceries go where on the shelf, and do things like setting the breakfast table. And so there's some great challenges for autonomous robots in this domain as well. So for those of you who are interested in sort of really big challenges in robotics, I encourage you to come to RoboCup. Oops. Sorry. And I've also, like many people, I've been inspired by autonomous driving. I had a car in the DARPA Urban Challenge back in 2007. And have thought for many years about what would the world look like when all the cars on the road are autonomous. This is a video from 20 years ago where what's happening is a multi-agent system where the cars that are white have a reservation to go through the intersections, and the ones that are yellow don't yet. But once they turn white, they have a guaranteed path through the intersection and won't collide with other cars. And we've thought a lot about what happens over the last 2 decades. What happens if you have human drivers and autonomous drivers working together? What happens if there's pedestrians or cyclists or multiple intersections? More recently, in this sort of autonomous driving sphere, my team at Sony AI had a landmark result that was featured on the cover of Nature, and it was that we created an end-to-end reinforcement learning agent that is able to drive faster than the very best humans in the task of Gran Turismo, which is a very realistic simulator. So what's happening in this video, the colored car is GT Sophie, our agent. The white cars are driven by people, some of the very best human drivers at this task who've put in their 10,000 hours to become experts, and ended up winning. It's the first time sort of in the series of results of AI agents doing better than people at something like chess or Go or Jeopardy or things. This was the first time that it was a real-time control task. And I'll let you watch it one more time. What I'm showing there is a skill that the agent learned by itself to be defensive, to basically stay in front of the human drivers to make it difficult to pass. So not just take the fastest route, but to take a route that was sort of taking into account the multi-agent interactions in this domain. And somebody once told me that if you want to really have impact with your research demos, have somebody with a British accent narrate the video, so that's what we did.
Hold their line and hold firm against the AI, but it certainly proved to be a tougher challenge than I should imagine that they were thinking. Emerald goes defensive then. Miyazono tries to get the switch back on the inside. No opportunity presents itself through turn 3 then.
Now this agent that we created, it was the scientific result that was featured as beating the human champions. It's now been deployed in the video game. If you have a PlayStation 5 and you have the game Gran Turismo, you can race against it. Thousands of people around the world are. It's, I think, one of the biggest commercial applications or deployments of an end-to-end reinforcement learning agent out there. I'll say just a very little bit more about that in this talk, but I'm not going to. I have a full 1-hour talk on how that works on my webpage if you're interested. And then another domain that's inspired me a lot is the domain of social navigation, social robot navigation. And this is, which is, not just having a car that can drive in lanes and be following traffic laws, but can deal with the sort of very sort of amorphous and open problem of navigating near people. And this is a collaboration with Joydeep that and a student and some students of ours where we had the robot go on a long-term exploration in Austin and just had to deal with whatever people were doing and sort of figure out where to move around them. And we're inspired by trying to do this not only on that path like that, but also in really dense crowds, like between classes or after a sports event or concert lets out. So I said I'm not gonna say much more about GT Sophie. I will say though that in the event that was covered in Nature, we learned a specific controller for each car track combination. So when we changed the car, we had to learn a different agent. If you're interested in learning more, there's going to be a paper in the next session at just after this talk at 3:36 in Garnet 219. A talk by Bram Bruton, who was an intern at Sony AI, on a single policy that can generalize to drive around 500 cars in Gran Turismo 7. So a big advance from that result several years ago. Okay, so let me get to the theme of this talk. And I'll observe that there's a lot of focus these days in the community, which is really, there's fantastic research. So don't get me wrong. I'm not trying to say we shouldn't be doing this. But there's a lot of focus on how to learn. And what I'm going to say is I think that it's perhaps overrepresented in our community. But you know, there's some great research on neural network algorithms for transformers, state space models, diffusion. Within reinforcement learning, there's many algorithms as well. And I sort of categorize the research in this space as sort of being of 4 types. There's developing new algorithms. There's what I call neural net psychology, which is sort of doing empirical tests to see under what conditions do these models and algorithms succeed or fail. There's also neural net neuroscience, where people look in and when are the nodes in the network being activated. And also neural net applications, trying to understand what they're good for. And again, really important, valuable research. But I'm going to give 2 pieces of advice in this talk for especially the students in the audience, one here at the beginning and one at the end. And the first is, be different. Okay, the fact that there are so many people doing this is I think, an opportunity for people coming into the field to try to do something different. Don't just, you notice something in common here, it's all neural networks. Don't just think about neural networks. Think about the paradigms from AI of symbolic reasoning, probabilistic reasoning, or maybe come up with the next paradigm that's going to fix some of the known problems with the neural net paradigm. And then the theme of this talk especially, don't just focus on how to learn. I think we need a lot more emphasis on creating programs or agents that for themselves figure out what to learn. And I take inspiration in this partly from humans, as many of us do in AI, from human babies. Some really inspirational work from my colleague, Karen Adolph, who's a psychologist at NYU at New York University. And she's noticed that a lot of research in her field tended to tell, or sort of dictate for the babies that are learning what task they have to do. In this case, they're enticing babies to just walk straight, starting them at the start of the mat, checking their footsteps, studying how they learn to walk when they're effectively told what task they need to try. But her observation was that really babies learn through their own curiosity, and that when they're learning to walk, they rarely just walk straight ahead. They're moving around in different directions. They're choosing when should they work with the stroller, when should they try something else they play around with. And in particular, they're also falling over a lot while they're learning to walk. And so we've actually collaborated on a connection between her findings and robotics. We have a paper in developmental science recently called Walking and Falling, using robot simulations to model the role of errors in infant walking, where we took the trajectories that the babies take in her lab and used them as the trajectories for our simulated robots to take while they were learning to walk, and found that they learned much more robust and stable walks than if they just practiced walking straight ahead, as many do when they're training their robots. Okay, so I've said that I think we should be focusing more on what to learn. Throughout this talk, I'm going to identify, sort of categorize some of the research that I've done in my lab, and I know that many in the community have also been doing. I'm not at all going to claim that I'm the only one to be working on what to learn, because now I'm introducing sort of how I've organized a lot of the research that I've done in my past, and also present opportunities for the future. And like I say, I think there's many people who are thinking along these directions as well. So there's 4 ways and 4 opportunities I think we have to identify what to learn. First of all, sometimes the task is too difficult, or the world is too big to be able to just learn straight from inputs to outputs, and we need to decompose the task in some ways. Sometimes the agent's future tasks are unknown, and it has to figure out what to learn now to predict what's going to be useful in the future. Sometimes there's other agents in the environment, and you need to figure out with whom to learn. And sometimes there's humans reacting to the agents, and you need to figure out what can you learn from those human reactions. And so I'm going to talk a little bit about each of these. And a warning here, I'm going to tell you a very little bit about a lot of different things, but then I am going to go deeply on just 1 or 2 things where I get into some technical detail, and I'll tell you when that's about to happen. So I'll go through these one at a time. First, when you're in difficult tasks or big worlds, so again, like you could have a task that's too difficult to learn right away. There's a long history of decomposition in a different way. In many different ways. There's simplification and then using transfer learning to first learn a simple task and transfer that to a more difficult task, or task decomposition. And we want to go beyond that into automated curriculum learning, where an agent is for itself figuring out what tasks should it train on. We've also thought about what occurrences to focus on. That's played a role in GT Sophie that I was talking about. And then also there's sometimes when the world's so big that you have to actively figure out what not to learn. So one at a time. First, the program chair, the one who was did me the honor of introducing me, Matt Taylor, his thesis from several years ago was the first to look at transfer learning for reinforcement learning. So this is task simplification, where he showed that you could dramatically improve learning if you start by learning a simple task and then transfer it to a more difficult task. And then my own thesis from even longer ago introduced layered learning, which is about task decomposition, where you have a difficult task and you break it down into sort of subparts and then put them back together. And then Patrick McAlpine more recently did this very dramatically in the robot soccer domain, where he put together 19 different behaviors into an agent that was able to win dramatically in the RoboCup 3D simulation competition. And ours is the red agent here, where it's learned to walk and kick and approach the ball and pass and do all of the things it needs to do to play a game of soccer. But both that transfer learning work and the layered learning work, the simplification, the decomposition was manual. What we've done more recently in the thesis of Samit Narvekar and follow-up work by Zifan Shu is what we call automated curriculum learning. We observe that people learn via curricula, and we're inspired by Quick Chess, which is a beautifully designed game to teach kids how to play chess, where it introduces one piece at a time until you get to the full game. And to do that, we observe there's sort of three necessities. First, you need to figure out what are the possible set of tasks to give the agent, and then how will you sequence them? What order should you present them in? And then do the transfer learning from the simpler tasks to the more difficult tasks. And the goal here is to learn a general teacher agent, the agent that can figure out how to create and sequence those tasks for the learning agent. And so Zifan recently introduced, observed that like if you have a robot and you want to do curriculum learning, the sort of standard curriculum learning would be you have a target task, like the robot starting at the red dot and getting to the green dot. You could imagine a curriculum where it sort of backs up to the orange dots that are farther and farther away. What we really want is sort of the meta version of this, an automated curriculum learning agent that, given a target task, can figure out what the curriculum should be for your agent, with the key insight that it shouldn't be a static one-time curriculum that works for all different agents, but rather the next task you present should be a function of what the agent knows now. In the same way that a really good teacher doesn't just teach their students all the same way, but will look at an individual student and say, here's the concept you're missing, here's what you need to learn next. And so we created a system that allows autonomous agents to do that. The problem definition is that we created an underspecified domain where we could parameterize the whole set of tasks. The student's knowledge, its current knowledge state, is characterized by how well it does on the target task right now. So you can have it test on what you're trying to get it to do and see which parts of the task it can do well or not. And then the teacher has to select from this distribution of tasks, not just for a fixed target task, but in the meta-curriculum learning problem, for a distribution of target tasks. So whatever the agent's currently trying to learn, it has to look at what the agent can currently do and figure out what's the next task it should give it. And we did this using a recurrent neural net, where the contextual information contains the training histories. In particular, how much training on a subtask improves the learning agent's performance on the target task. And if you get a lot of experience over that, then you can figure out, okay, in this current state, what's the target task that will give the biggest boost, or the subtask that will give the biggest boost in performance now. And we have some results in a recent paper showing that using a metric of iterations to threshold, so how long does it take before the agent's able to get to a threshold target performance in a number of different domains, it's able to do much, much better than sort of the competing automated curriculum learning algorithms, both in sort of a toy domain and in a more sort of realistic simulation of habitat. We've also looked a little bit, I'm not going to go into detail on this one, at event tables, but it did play a role. This is in with my colleagues at Sony AI, it played a role in GT Sophie, where for those of you who know some of the details of how reinforcement learning works, we were using an algorithm called soft actor critic that uses an experience replay buffer, which you can think of as sort of keeping in memory the experiences that you want to train from. And we found that it could be very critically important to get the right experiences into that replay buffer. And in particular, those associated with sort of well-defined events, like when our agent is behind one car or two cars or three cars or many cars, or specific parts in the track, and that the mix of experience needed to be very carefully curated for the, based on where in the track the agent was. And then we came up with ways to automate this process as well. So it's a sort of, in effect, trying to figure out what occurrences to focus on. And then just for the last part of this section, the thesis of Todd Hester, more than 10 years ago, took the observation that sometimes the world is so big relative to the length of time that an agent has to exist, that you just can't explore everywhere. And often the assumption in reinforcement learning has been that the world's relatively small, an agent can exhaustively try everything and then figure out what's the best thing to do. But we as people are very familiar with this concept of our life being short compared to the size of the world, right? I can't visit every city in the world even once in my lifetime. I can't even try every restaurant in the city that I live in. I have to decide actively what things I'm never going to try. And so an algorithm, the TextPlorer algorithm for targeted exploration was actively doing that based on only exploring states that are both uncertain, where you don't know what's going to happen, but there's some promise that a good thing will happen if you go there. You don't need to explore the ones you're uncertain about, but are pretty likely to be bad. Our landmark result on this was we took our autonomous car from the Urban Challenge and learned a speed controller that where it started from scratch. It didn't know what would happen if it pressed the accelerator or the brakes. And it was trying to maintain a constant speed of 30 miles an hour. And in just 3 minutes of driving, acting at 20 hertz, so about 18 episodes, it was able to learn a controller that's as good as a finely tuned PID controller. And basically by figuring out it never had to explore things like flooring the accelerator or slamming on the brakes and the accelerator at the same time, but rather focusing its exploration. Okay, that's the first segment. So sometimes I've said when the agent's task is too hard or the world is too big, you might need to do task simplification or decomposition, and automated curriculum learning does that in an automated way. You might need to identify what occurrences to focus on using, for example, event tables, or you might need to learn what never to explore, for example, as TextPlorer does. Another situation, and this is where I'm going to go into a little more technical detail, is when the agent's future tasks are unknown. So this is also something that we're familiar with human learning. We often put our babies in a crib. They have to explore what to do with the blocks and things, but they don't know what they're learning for. They don't know what tasks they're going to be given. They don't know yet that you're going to ask them to set the table or fold the laundry in the future. They're just learning how the world works. And so we'd like to also think about how do agents figure out how the world works before they need to do the tasks. And so in this segment, I'll talk very briefly about causal reinforcement learning, where and then I'll go into a bit of detail about trying to have an agent figure out what action space to learn with using an algorithm called SLAC. I'll talk briefly about continual learning and then go into a little more depth on unsupervised RL. So first of all, causal reinforcement learning, the idea is that what the agent needs to learn about before it gets its tasks is which objects cause changes in other objects, or which actions cause changes in other objects. So, to learn that, this might be the first time that I'm exactly this distance from that plant, but I can't cause any changes to that plant when I'm this far from it. On the other hand, when I'm close to it, the actions I take could cause changes. And so we have a number of different algorithms with a few different students working on this. And both looking at the different action spaces, different state abstractions, or also local dependencies for an intrinsic reward to guide reinforcement learning. And I'm not going to go into details on these, but the papers are all available online. What I will talk about in much more detail is sort of a similar setting where what we're trying to learn is a latent action space. What actions are going to be useful for learning? So this is a paper I'm really excited about that appeared in the Conference on Robot Learning just a couple of months ago. The first author is Jiaheng Hu, co-advised with me and my colleague Roberto Martin. And the idea of SLAC is that it's going to learn visual motor, contact-rich, whole-body mobile manipulation with what we call real-world reinforcement learning without a single demonstration. So much of the robot learning literature these days focuses on, well, actually, first I'll show you, like the kind of task we would learn on a robot, for instance, trying to wipe a whiteboard while navigating around obstacles like this trash can, where it has to control its camera, its arm, its base. That's the whole body aspect of it. So why real-world reinforcement learning? A lot of the robot learning literature these days addresses the difficulty of whole body manipulation in one of two ways. Either by trying to learn in a simulator that's high enough fidelity that you can just learn in the simulator and transfer to the real world. But that can be very challenging because it's difficult to build really good simulators, especially for complex tasks. Or they use imitation learning. They have a person or another robot do the task with teleoperation, but that can be very costly to collect high quality demonstrations. So our goal was to try to enable a robot to quickly and efficiently, just in the real world, learn without any high fidelity simulation or demonstrations. Now, the existing state-of-the-art real-world RL will just do what you give it the task of wiping the blue mark, and it's just going to do motor babbling. It's not even going to find actions that give it any reward at all because it's got this complex action space and a very large state space. It doesn't learn anything meaningful. So the question is, how can we overcome the sample efficiency and safety concerns when doing this in the real world? And the insight here was that the action space is key, and that and a good action space will both facilitate sample efficiency and safety. And we can learn a good action space in a low fidelity simulator, one that's much easier and cheaper to obtain than a high fidelity one, where we take we abstract the high dimensional action space into this low fidelity low fidelity simulator and learn the action space. So here's an example for that robot I just showed you, a low fidelity simulator. It's not nearly good enough, like I say, to directly transfer zero shot. But the goal is to use unsupervised reinforcement learning to explore before you're given the task, to learn a task agnostic action space that will work for any downstream tasks. And so we do that by learning what we call a latent action space that's low dimensional, encoded here, where the latent actions I'm going to represent as Z, and then there'll be a decoder that translates those to the motor commands to the robot. And there's been work already out there on learning diverse low-dimensional actions, but a challenge with it is that they often learn what we describe as entangled actions, ones that a single dimension in your action space will change lots of different things about the robot. So it might move both the base and the arm, or the base and the head, the camera. And what we'd like instead is an action space that's disentangled, so that you can have certain action dimensions that move just the base, or that are, which might reflect some aspect of your reward function, some that just move the arm, some that move the camera, in a way that's sort of very controllable. And so, so that's what I just set up here. And so we can learn this using an algorithm that we invented called DUSTI that appeared in NeurIPS a couple of years ago. That has a particular loss that encourages this disentangled low-dimensional action space. And it's easily combinable with a safety reward that'll penalize things like actions that cause the robot to collide with itself or do something else dangerous, like going to the edge of the environment or falling off of something. So how do we do this? We take this, the latent action decoder is going to be sending actions to the robot, and we want to try to identify different dimensions, or learn an action space that will have some dimensions that control the camera, some that the arm, or some the base. I'm using this as an example. The robot actually for itself figures out what are the relevant dimensions. So we don't tell the robot that you want to separate into the things that are illustrated here, but these are human understandable dimensions. And we do this using a reward function that encourages this disentangled sparse action space. And then we can add a safety reward to our learning objective as we're learning this action space. And then we'll be able to use this in step 2 for learning a downstream task, freezing that sort of general purpose action space. And we developed a factorized version of soft actor critic that leverages the structure of this space, especially when you have a factored reward function. and certain action dimensions are going to affect some certain aspects of your reward function. So it can be very difficult if if your actions each affect every component of your reward function, but in many tasks, there'll be sparse dependencies, especially if we learn a good action space, so that there's many fewer connections or sort of effects to learn, which allows for much more efficient reinforcement learning training. How do we learn the dependencies between the actions and the reward terms? Using a conditional mutual information model that basically gets experience and identifies which changes lead to observable changes in your reward terms. And the details are all in the paper, but what comes out is a matrix that basically can be read and say, if you want to affect the base of the robot, then here's the actions you care about. If you want to affect the camera, the arm, etc. And by the way, the experience that you use to learn these dependencies can also be used to seed your experience replay buffer when you do the downstream learning. So then when you're ready to learn a task, when you're done with learning your action space, you freeze this low dimensional action space so that it's no longer being learned. And now you learn a task policy for your reward function that also leverages that causal matrix from the previous slide to maximize along your reward terms along different dimensions. And so the punchline here is that we can learn task policies. Here's a robot at the start of training, so it's not able to learn wipe the blue marks, but you should notice that it's now exploring sort of much more efficiently than the previous video I showed you. It's not just motor babbling. And after 40 minutes of training, it's now able to completely wipe the board. It's getting a reward signal for just wiping these blue marks, and so it's able to control its base, its camera, its arm to wipe the board down. And again, all of the experience happened in the real world. It can also use exactly that same action space, just a different reward function, to do things like pushing garbage into a tray, like as shown here, or to sweep garbage into a bag. And there's detailed results in the paper, of course, but the key is we compare against just going zero-shot sim to real. That doesn't do very well at all. Some other real-world reinforcement learning methods, and we do both dramatically better in success rate and in many fewer safety violations. And the key is that all of those policies I just showed you the videos for trained in less than 1 hour. So again, there's many details online. Also within this, when you don't know what downstream tasks there are, that's sort of the whole area of continual learning or lifelong learning that has a rich history in the AI and machine learning community that we've done some work on in my lab, and it actually was the theme of Cogitai, the startup company that sort of eventually transitioned into Sony AI. I'm not going to talk about that in detail, but I will go into a little detail as well about some work that I'm excited about on unsupervised RL, where you have a pre-training phase, just like we did in Slack, but that it does this in an even more sort of theoretically grounded way. And so this is again, in a setting where the robot has a pre-training phase where it can just get environment interactions and learn what you could think of as a world foundation model, something that's just detailed knowledge of how the world works. And then once you've done that well, ideally, once you're given a reward function, which could vary, you can just very efficiently almost look up what's the optimal policy for that reward function. And that's sort of the inference phase. The observation is that a single environment can support lots of optimal policies depending on what your current reward function is. And in fact, in a paper from ICML this past summer called Proto-Successive Measure, representing the behavior space of an RL agent, we noticed that, again, for those of you familiar with some of the reinforcement learning terminology, a successor measure is a measure over the future states visited when executing a given policy. In the reward-free phase, you're trying to learn, basically, if you execute a particular policy pie from a particular state and action that you start with, what's the distribution or the visitation distribution of the next states that you're going to arrive at in the future? Those are the S+. And you want to learn that for any given policy, such that once you're given a reward function in the reward-based phase, that you can just look up the policy that visits the states that are rewarded by that reward function. the most. So this has nice properties. There's reward-independent representations and a linear objective for policy optimization. We actually show in the paper that if you consider all of the possible optimal policies that are supported by this environment as a function of different reward functions, that it forms an affine space. So that we can then do a very efficient search when you're given a reward function to the policy if you've explored this, in the pre-training phase, the successor measure efficiently. And again, this is joint work with a couple students, Siddhant and Harshit, and also my colleague Amy Zhang. One thing that this has allowed us to do is to incorporate language into zero-shot reinforcement learning with a method called RL0 that has 3 different phases. It uses a fine-tuned visual language model to generate visual trajectories based on language commands in the target domain. Actually, I'm going to have one slide for each of these phases, so I'm not going to read this slide to you. But there's an imagine, a project, and imitate phase. So imagine is you take a phrase like a person doing yoga, use a pre-trained video foundation model to come up with a sequence of what that looks like. That's sort of imagining what these words should map to. Then there's a project. A project phase, because what it imagines might not be realizable with the hardware of your current robot. So you need to do a similarity-based retrieval to sort of come up with a sequence that the robot can do. And then we can use these proto-successor measures to come up with the policy that matches the distribution that was projected. And so, so for example, if we ask for a cartwheel or crawl like a worm or a bunny hop or jump high, this was the only input after the proto-successor measure phase. Just we gave it this language and it's able to do these without additional training, just by, so that's why we call it RL0. It's sort of zero shot from the words to the behavior. And we actually showed that we can even skip the imagine step, which enables cross-embodiment imitation by leveraging demonstration videos from YouTube. So that if we just, if we don't give the words, but rather give a demonstration of what the person is doing, we can learn policies that will mimic those fairly effectively. Okay, so this second phase of the talk I talked about, and I went into some detail on here, on what an agent can do, the opportunities for what to learn when the future tasks are unknown, when there's a distribution and you have to leverage information from the pre-training phase. And in particular, I talked about causal reinforcement learning for learning state dependencies, SLAC for learning the action space, continual or lifelong learning, and then unsupervised RL. I'll go a little more quickly, I know in the interest of time, through these last 2 parts, but I'm going to first talk to you a little bit about what an agent can learn when there's other agents in the environment. And this is joint first authored work by Caroline Wang and Arash Rahman on open-ended training for ad hoc teamwork. So first, what is ad hoc teamwork? This is a problem that I've been interested in, and this is to try for with whom to learn. But ad hoc teamwork is a problem that I've been interested in for about 15 years, a little more, on trying to come up with an individual agent that can collaborate with teammates that it's never seen before. So they may be programmed by others. Their teammates they're likely to be suboptimal. We don't have any control over them. Some of the first PhD theses in this area were done by Sam Barrett and Katie Genter. There's also been contributions by Noah Agman, Stefano Albrecht, and several other students and postdocs in my lab, some of whom are here in the audience. And the observation is that people can do this very well. I can go play a game of pickup soccer with people I've never seen before, maybe even in a country where I can't speak the language, and figure out very quickly how to collaborate with my teammates. Or if there's a disaster rescue scenario, people can come together and figure out how they should work together, even if they're total strangers. So our goal has been to try to create a good team player that's an autonomous robot or autonomous agent. I first introduced this as a challenge problem at AAAI 2010, and since then there's been some theoretical results, there's been some experimental results, and actually I won't show those right now. And so this more recent work is on trying to update the paradigm to really learn with whom to learn from, and it's in this theme of what should you learn. So much of the existing research in ad hoc teamwork breaks the problem or the solution into 2 phases. First, a teammate generation phase where you pick your teammates that you're going to train with or practice with. And then with those teammates, you're going to learn a general purpose policy. But it can be challenging to figure out how many teammates to generate, and it can make, and you don't sort of get this feedback loop that we also have in automated curriculum learning of being able to take what you currently know and figure out what you should learn next. And so in this paper, we've introduced what we call open-ended ad hoc teamwork, where we frame ad hoc teamwork as an open-ended interactive learning process between a teammate generator and a learning agent that closes this loop and doesn't just generate teammates once and for all, but rather looks at what the teammates that the agent is currently good and bad at cooperating with, and then picks the next teammate to add to the sort of the set of training sparring partners or training partners. And the theoretical construct we use this is trying to maximize cooperative regret, which is identifying a teammate with whom it's possible to cooperate well, but with whom we don't currently cooperate well. So it's not going to be worth it for me to practice with a teammate who's just, whatever they do, they just sabotage my behavior. They're not going to be a good teammate. There's nothing I can do. What I want is one where it would, there's a way to do well with it, but my current agent isn't very good with this teammate. And so that's what cooperative regret maximizes. And so we have an algorithm called Rotate, which will generate a teammate, figure out what types of teammates it's bad at cooperating with, train with them, and then repeat in an iterative loop. We show these, we sort of diagram this with chefs because our main evaluation domain is the overcooked domain. We also use level-based foraging. But the main result here, again, blue, our agent is in blue. And it does dramatically better than the Minimax approach, which is sort of an adversarially robust policy that protects against the worst case teammates, and does better than many of the other ad hoc teamwork types of agents. And on the right, we see that it learns a very balanced policy. Rotate is shown in purple, and it's showing how well it does against different previously unseen teammates. And it's sort of, there's some other algorithms that learn sort of specialized policies. Rotate learns one that's able to cooperate with anybody. Okay, so that's the third segment. And then the last segment is what happens when there's humans in the environment and there's an opportunity, then they're reacting to the agent and you might want to learn from them. And so you have to figure out what to learn from them. And this is based, I'm going to talk about very briefly about, actually, I'm not going to go into much detail on this at all, but I'm going to talk a little bit about some groundbreaking work from the lab on evaluative feedback, then talk about what happens when people give various different types of input, and then finally talk about what happens if the people are even not explicitly giving feedback, but just implicitly. So first, Tamer, which is a system called Teaching an Agent from Manual Reinforcement. It was the PhD thesis of Brad Knox and was later followed up by Garrett Warnell to bring it to visual input in a system called Deep Tamer. Like I said, I'm not going to go into detail here, but I think the important feature is that this from almost 20 years ago was introduced this concept of what now has become called reinforcement learning from human feedback, which many of you know plays a big role in training large language models. And so I think Brad really deserved that claim to fame. And then later on, we've looked at, and the idea here was that a person is just giving evaluative feedback, so good job or bad job, sort of a thumbs up or thumbs down. We've looked at more recently what happens when people give various different feedbacks. And so with Shuisu Zhao, who's now faculty at George Mason University, we looked at the task of learning robot navigation in highly constrained spaces. So rather than a robot in sort of an open floor plan, what if it needs to navigate through spaces that are barely bigger than the robot? And we observed that for this, we can leverage in a particular way various different types of human input, either demonstrations or corrective interventions where a person is just watching the robot and jumping in when it thinks the robot's done something wrong, or evaluative feedback, more like the Tamer setting where it's saying good job or bad job, or the agent can just learn on its own using reinforcement learning. And the key here is we put Shuisu and I put them together eventually. Well, first of all, those different paradigms only differ in how you learn from the different types of human interaction. There's sort of a high-level algorithm that just differs whether it's a demonstration or intervention or evaluative feedback. But then ideally what we would like, and we've made progress toward, is being able to take whatever feedback is given and learn from demonstrations when that's what you have, interventions when that's what you have, evaluative feedback when that's what the person's doing, or perhaps then going back at night and using reinforcement learning to synthesize all of that and create a new behavior the next morning for the robot in your home. And then finally, there might even be situations where the person isn't explicitly giving feedback, but rather you're learning from implicit feedback. So if you're an autonomous car and your passengers look like this, you probably don't need them to tell you that you've done something wrong. You should be able to learn from their facial expressions or body language that something wrong is happening here. And of course, there's also the analog of positive, positive facial reactions or body language. And so we introduced a system that was introduced at Coral a few years ago called Empathic, Evaluative Mapping for Effective Task Learning via Human Implicit Cues, that introduced a novel framework for this learning from implicit feedback. And it has two different phases. One where when we know what good behavior and bad behavior is, we can learn a mapping from a particular person's implicit body language and facial reactions to what are the good signals and the bad signals. And then once that model is learned, we can use that in sort of a tamer-like system to just watch their body language and learn the behavior that the person wants. Okay, so that gets us through, and I know this has been a bit of a whirlwind, but like when we have humans that we can react to, we might want to learn from evaluative feedback or various different types of input using Apple or implicit feedback using Empathic. And this sort of brings to a close this sort of cataloging of different opportunities to identify what to learn. Sometimes the task is too difficult or the world's too big. Sometimes the tasks are unknown and you need to use unsupervised reinforcement learning in a pre-training phase. Sometimes there's other agents in the environment and you might want to learn with whom to train, who should the sparring partners be, and sometimes humans react and you need to figure out what to learn from the people. So just as a reminder, this all fits into my research question, the larger one that I introduced at the beginning. And just to close, I said I would give two pieces of advice, especially for the students in the room. The first advice from the beginning of the talk was be different. Don't just study neural nets. Again, valuable research, but it's not the only thing. And especially think not just about how to learn, but what to learn. And then my second piece of advice is in today's day and age, it's really essential that we all consider the societal implications of our work. AI is changing the world in many different ways. AI algorithms are. And so I think this is really essential right from the beginning of your career. When I started as a student, it was less of an issue because it seemed much farther from the algorithms we were working on in the lab to changing the society. But now that's happening all over the place. I mentioned at the front of the talk the 100-year study on AI, which again I think we should all be watching for this year's study panel report, which will be the third one. They're coming every 5 years. I talked about some AI education at the beginning. I also have materials online for a new course that I developed with a humanist colleague from the humanities, with a humanities background on ethical AI and robotics. We recently published a paper with Brad Knox as first author, but that collaborated with some social scientists and psychologists that catalog the various harmful traits of AI companions, which is a really big issue in the news these days. And then finally, with my team at Sony AI, we had our second paper that hit the cover of Nature just a month ago, called Phoebe, a fair human-centric image benchmark. That Alice Zhang is the first author, but it's a large team effort. And this is the first data set that's really collected in a very, what we argue is an ethically sound way, and we define in the paper what that means. It's not large enough to be a training set, but it can be used for evaluations. It includes thousands of images, very geographically diverse. And the key is that, one of the keys is that the annotations of people are not done by an external observer, but rather the people themselves can say what's their nationality, what's their gender, where are they coming from. It's built in what we define and hope people will emulate an ethically robust way where people are compensated for their data. They can always choose to remove their data from the file. And it's made for ethics evaluation. It can, it's enabled bias analyses both in small models and in foundation models. And I'm just going to close by showing a brief video about it.
A lot of ethical issues with computer vision start at the data layer.
And that data is not collected in an ethical and responsible way.
The internet is already skewed towards certain demographics.
You know, white, male, Caucasian.
It can warp things.
We want to fix that. We need to have a technology that is fair to everyone.
Ethical data collection turns out to be an extremely challenging issue.
It's one of those things that you think this shouldn't be that difficult.
Phoebe is the first data set of its kind.
We are pushing forward the boundaries to create this for the community.
It's very important that the whole community builds the AI on a foundation of ethical data.
So, so with that, I would just like to say that all of this work is based on some fantastic and important contributions from all of the past and present members of my Learning Agent Research Group at UT Austin, my fantastic colleagues at Sony AI. It's made possible with sponsorship from several different government agencies, private companies, the Good Systems project at UT. And with that, I thank you very much for your attention. I'll be more than happy to take questions.
All right, if you have questions, there's microphones down front. You can come and introduce yourself with your affiliation. Oh, we've got a question over there on the left. Yes.
Michael O'Riordan, Cork, Ireland. I really enjoyed that, and congratulations on your amazing contribution over the years. Can I ask you where we're at with autonomous robotic surgery and where that's going?
Yeah, so that's a great question. I haven't personally worked in robot surgery, but we do have some faculty at UT Austin, in particular Farshid Alambeji, who is and Anne Fay, who are working directly with surgeons on various different ways of using robots for surgery. The most famous robot for surgery is the Da Vinci robot, which has been used sort of for teleoperation for surgeons for a long time, and is very well deployed. But now I think there's a lot of progress that's going into starting to make it semi-autonomous, to allow the robots to do some of the suturing on their own, or to use, and this is again the work of Anne Fay, which, to use robots to help train people to diagnose or to understand what expertise is, and then have robots to help learning surgeons get that expertise more quickly. Farshid, my colleague, has been working on ways of making colonoscopies less invasive by having robots sort of travel through your digestive tract. And so I think there's been a lot of really exciting progress. I can't talk, none of it that I've been directly involved in, but I think it's a really exciting moment for robot surgery, and definitely an area that I would encourage budding roboticists to focus on. Hi, Manuela.
So, hi, Peter. So, I've known you for a long time, as you know, and I am people probably see this talk for the first time, but I want to say that this is an amazing talk, and kind of like thank you for sharing with us these enormous kind of like contributions and interesting things to work on. I mean, I feel I could go back and advise 10 PhD theses in many of the things you've raised. But I wanted to ask you one thing, if you could further share with us, how do you, in your group, with your students, generate problems to work on?
Yeah, so first of all, for those of you who don't know, Manuela was my PhD advisor, is still my advisor in many ways. I go to her for advice all the time. And actually, thank you for giving, I know this isn't the answer you were going to, you were fishing for, but I've learned from you. I had the immense benefit of having a PhD advisor that let me follow the problems that I was interested in. I wanted to do robot soccer. You and Manuela had never done robot soccer. I said this would be a great problem to focus on. You said, yes, let's do it. And so I have to admit, And I'll just have to admit, I'm very proud to say that I've paid that forward. And almost everything that I've shown here originated from the ideas of my students. This is not me telling them what to do. This is me giving them the freedom to suggest to me what to do. And often they've had to convince me. So I can say, the autonomous intersection work that I showed at the beginning was the work of Kurt Dressner. That was his idea. In fact, it was because he came to a meeting for me with me and was late and was stuck at an intersection at a red light. And he said, we can do better than that. And he pitched it to me. Brad Knox on Tamer, I told him, I don't want to do reinforcement learning with people. How are we going to even define the problem? He just kept pushing that this was going to be a good problem, and it's been one of the most influential things that come out of my lab. So I find that the way I define the problems is create a supporting network for my students, and I've learned that from you.
So the next technical session is starting in just a few minutes, so we can close this session. However, if people would like to stick around, Peter has generously agreed to continue answering questions. Please continue to come up to the mics and we can keep talking. But if you do want to attend the next technical session, you should probably leave nowish.
And I won't at all be insulted if you leave. In fact, I encourage you to go to the next session. But like Matt said, I'm happy to stay here and answer more questions.
Go to the next session and see your paper?
Yes, or there's so many other papers as well, please.
Hi, Peter. I'm Ritvik. I'm a PhD student from University of South Carolina. My question is to ask about the evaluation metrics that have been, been a topic of discussion, especially when you're trying to look at multi-agent systems for enterprise integration. What would be your take on the next gen of evaluation frameworks that need to be built for these systems?
Yeah, I think evaluation frameworks is something that's really important. In fact, there's been a lot of benchmarks that are put out there, and I think those can be very valuable, but they also are fraught. There's challenges with benchmarks in that they can cause people to sort of overfit to the tests. We get lots of complaints that we keep moving the goalposts of what it means to be doing doing AI. So I think this is something that's sometimes people ask what are the roles for academia versus industry. I think this is something that was suggested on a panel I was on just the other day. So I'm not the only one to think this. It may have been I think Shlomo Zilberstein who was suggesting this, but that it's a great opportunity for academics to be proposing and defining those benchmarks or those evaluation frameworks that can be then sort of independently audited, and that I think we need varied evaluation metrics, right? We've learned over the years that intelligence is not one thing. There's not a scale of intelligence that goes from 0 to 100 that we're climbing up, but rather there's ability to do image recognition or natural language processing, physical manipulation, spatial reasoning, so many different things. And so we need evaluation frameworks that can capture those nuances.
Thank you.
Hi, I am a postdoc at Los Alamos National Lab, and I would like to ask about when these models are able to cooperate. You said that you have a way of identifying if two different models are likely to be able to work together. Is there any understanding of how the phase space of this looks, such as something analogous to temperature, where maybe lots of erratic behavior, any transition?
Yeah, so there's in the multi-agent systems community, I'll point to the work of Carl Tuils and others. There's a notion of replicator dynamics that has looked at, when you have multiple learning agents, what are the different phases that they get into, and when do they cooperate, or what kinds of there's sort of graphical ways of representing that. Again, not my work, but there's a long history in multi-agent systems. Many people think that agents just were originated in the past year or two, and multi-agent systems is still being invented. But really, multi-agent systems, the first conference was more than 25 years ago. Autonomous agents was even before that. And there's a rich history in looking at sort of what happens when multiple agents learn together in various types of tasks and control tasks, and it needs to be updated to now think about, what if you have different large language models or neural networks models learning together. It's not clear that everything from the past will apply directly to the current settings, but there's a lot to learn from by looking back in that literature. And I think, like I say, I think replicator dynamics is one of those methods that others have studied more than I have.
Hello. Yeah. Hi, Professor. Thank you so much for a wonderful talk. I am from Sony Research India, from user engagement team. My work primarily involves causal inference and causal discovery. So my question is on the meta learning part that you explained, which was about this curriculum learning. So did you observe that these teachers that are teaching the agents, they fall into their own bias and traps and kind of create an echo chamber which will limit their ability to transfer the knowledge for further learning, something like that?
I mean, our objective was to personalize the learning, right? So our goal was to look at curriculum learning as a process that should be specialized towards the current agent that you're training. So our objective in that case was not to learn necessarily a curriculum that would generalize to all of the other agents. And I think, if we just used exactly a fixed same curriculum over and over again, we might end up in a local minimum. So I think that's a point to consider. But our objective has been to learn just like an individualized teacher, this sort of dichotomy or this interaction between the learner and the and the curriculum generator that is a specialized pair. And so I think what you're suggesting might be a different direction to take the study in that we didn't.
Thank you.
And I apologize. I forgot there was very little buffer between the next invited talks in this room. So unfortunately, we have to close this down so that our invited talks from Singapore can come. However, maybe Peter would be willing to wait to ask a few more questions out near the door.
I'd be happy to.
Thank you so much, Peter. Thank you for your questions.
Thanks.